Hello everyone, this is Astarag and I'm starting a new playlist on learning distributed training of language models from scratch. Here we'll go from theory to implementation details and implementing stuff from scratch. This is the syllabus for this course. We'll first start with data processing, then we'll go to data parallelism, tensor parallelism, context, and pipeline parallelism. And these are the algorithms that we'll be covering: supervised fine tuning, DPO, and GRPO. Recently, I came across this library called as RL2, which is Rayless Reinforcement Learning, and it has a really good implementation, a reference implementation of 3D parallelism, and which we'll be referring a lot in this set of tutorials. So let's in this video we'll be mainly going over data processing. So how are this data formatted to language models, and we'll learn all the details about it. So here I'm starting out with transformers tokenizer, a Qwen 2.5 1.5b instruct model. I have loaded the tokenizer, and then I have a piece of code which initiates a data loader. It's a simple PyTorch data loader, but there are some nuances that we would first like to go through. Before jumping into PyTorch data loader, it will be helpful to understand what is the difference between an iterable and an iterator. In Python, iterable is something that you can loop over, like a list or set or tuple. So if you want, to exhaust the entire list, you can loop over each element and get back. Also, it also implements a get item dunder method, where if you say I want index 50th of the data, then you will get back all the results from there. But on the other hand, iterator is something it is a generator, and here instead of implementing get item index, you have a next dunder method where you lazily load data from memory. So that way you don't have to keep the entire data set in your memory, and you can lazily start loading. There are some advantages of both kind of data set, where in iterable it's basically a map style data set where you can ask, okay, it's really good for debugging. You can see the 50th index of the data set or the 50th batch of the data set. You can inspect the examples. But iterated, like, you don't have a get item dunder method, so it's really good for lazily loading the data set. PyTorch has support for iterable dataset, but under the hood they convert each batch to an iterator, so that they can also lazily load and they don't have to keep the entire dataset in the memory. So so think about where would you need an iterator or this stateful cycle data loader where you have endless stream of data coming in. Suppose you are pre-training. In pre-training, we cannot do map style data set. Like in pre-training, there is no index based data set. Like you are continuously loading data from your memory, and then you are training the model. And this pre-training data set consists of like 15 trillion tokens. So going through with batches is kind of really having these indexes for each batch incurs a lot of overhead. So instead of that, you can just keep on importing the data till you reach the end of the data set, and then the compiler will give you a stop iteration error, and then you can just stop the iterator. So in those cases, actually, the stateful cycle data loader is very helpful. Like it will keep on loading the data and till it exhausts. And also going forward, we'll be having a lot of RL training, and in RL generally the step size is more important rather than batches, because like you will be filtering a lot of data set, or if you have heard about other algorithms, they do rejection sampling. So there is no concept of like having a fixed batch size. You may load in a lot of data and then probably just uh, train on certain batch size. So uh, so it's difficult to assign indices beforehand to the entire data set sometime. So that's why you can lazily load and have a iterator. So let's now jump into how does the data set look like. So this is OpenAI chat messages style dataset where you have a role, a system role, a user role, and assistant role. In system role, it's basically a high level instruction. It has a lot of details on not to be harmful and be faithful, and yeah, like these are all the high level instruction about the task. And user is basically the task, the user content. It's like what question are you trying to solve, and assistant is the response from the language model. So um, so here if you see, I loaded in the same messages data set, and then I using tokenizer apply chat template, I formatted this data set, this data point. You can see like the system comes in first, and then the user, and then the assistant. So uh, so this is how the singleton chat messages look like. Now let's see what kind of pre-processing would you do on this singleton chat messages. So in the RL2 library, they have these things. They extract this from the dataset. One is states, actions, action mask, EOS mask, and position IDs. States are basically the token IDs of all the system, user, and assistant prompts. So uh, if I have to go back here and base print tokenizer dot apply chat template messages, so this is states. So it's all the all the like system, user, and assistant prompts in a chat template format. Actions are basically the response. This is the part of the action, only the response string answer. As action mask is it is the thing that we will be calculating loss on. Generally we don't calculate loss on the system and user message, we only calculate the loss on the assistant prompt. So because these two things will be given to the model, and the model has to generate this. So it's just better to have only calculate loss for this part of the string. And EOS mask, uh, so here the if I check out the tokenizer.eos token, so this is the end of sequence token, and what you can see here, uh, this is the EOS token. So this is where the response ends from the assistant, and the EOS mask represent where is the response ending. Like it will basically give you the sequence length of the sentence, which includes, which will be basically the length of the states. So the EOS mask would be, so if I check the length of the states, it's 19, and EOS mask would be 0, 0, 0 dot, and on the 19th index it will be 1, which represent that we have a EOS token here. So this would be your EOS mask. And position IDs are basically or torch.arrange on the states, where so if I do so states are like, as we saw that the sequence length was 19, so position IDs would be 0, 1, 2, 3 till 19. So this position IDs would be relevant when we will dive into context parallelism, but for now let's just stay with let's just understand the pre-processing of that. So now we have to derive all these things from our singleton chat messages. So we calculated states, so we have states, and now we want to calculate the answer or the actions. So action is basically this answer token and this IMN token, because given the model will be given up to here. So if I show you what the model would be given, so I'm indexing till the last message, and so the model will be given till here. Also we have this special function called as add generation prompt equal to true, which will give you this assistant, which is the start of the assistant. So your model will be given this and it has to generate the next token. And if I remove the print, actually it will be much more clear. So this is what you need to find in the string. So suppose I take this part and remove the print. You see, so you need to find this part of the string, and after this whatever comes is the response from the language model till IMN and slash new line. So we have to find this part of this part, and then only we can calculate the actions to the language model. So before so this is what is called as a response template. IDs response template, and we can copy this part of the string to here, and let's try to see tokenizer.apply encode this response template. So these tokens correspond to this part. So from our states, as I showed earlier, if I try to map where this part is coming, it would be right around here. Sorry, yes, my bad. Yeah, so it would be here. So this is where up to this point the model will be given the token IDs till this point, and then it has to generate all these things. So the actions are basically this parts. They are not so this should be masked, and the model should not compute action loss on this set of tokens. It should only compute loss after this. So how can we find it? So this is the concept in Hugging Face that you might have seen called as data collator for language modeling. So you can, I'll paste in a code. So let's name this variable response template IDs, and let's import torch. So this would be all the matches. So what this code is doing, it is taking the states and building a length of response template, like a sliding length of response template. We saw the response template ID was of length 4, so it will take first 4, and then again it will take first next 4, and then again it will take next 4, and then again it will take next 4, and it will keep on rolling. So this is what this function is doing, and it is basically trying to match the response template ID in any one of this 4-4 pattern. So we will get the first response template ID, because we are assuming that there is only one response template ID in the entire prompt. So we'll just index the first one, and now you can calculate the action and action mask by this code block. So if you see the action the actions like start from the matching index, and then we add all the response template IDs, and whatever comes after that is action. And action mask is 0 for all of this uh, non-assistant part of the prompt, and it is 1 for rest of the actions. So if I just print these things, so as we saw here, like we wanted everything after this 198 token, so this is what we wanted, and this is the actions, and all of the states are 0 except for this set of actions. So we have basically built an action mask here. So if I also show you how does it look like, so uh, so this exclamation mark is basically 0. So if I okay, now let's go to another level of discussing from singleton chat to multi-turn chat. So this is like I pasted in some prompts like multi-turn chat conversation where there is one system prompt and there is a user prompt, assistant prompt with answer 1, followed by another user prompt, like there is a follow-up from the user, and there is another assistant response. So this is called as multi-turn conversations, and we will be basically training the model to learn to generate this given all of these things. So let's try to see how does the messages ticked look like here. If I So this would be a list of dictionary starting with system, user, assistant, then user, then again assistant. So if I apply chat template here, you can see like it's a multi-turn conversation of user, assistant, and after this IM end, then you get back user again. So let's apply similar concept in finding the response template ID, and here the response template ID would be this and this. So you need to find the last index, like the last response to template ID. So following following how we did for singleton chat, let's also do for multi-turn chat. And the only thing that you need to notice is here we are indexing by -1 or the last assistant message. So we are indexing by -1, as we are not going to train on this assistant. This answer will just be training for this one. So in the causal language model, the model will be given all of this and the model has to generate this. So multi-turn are generally used in chat sessions that you see in ChatGPT, or they can also be used like in few shot prompting. In that case, like we don't want the model to learn the few short responses. We want the model, given the few short responses, generate this, the answer to response. So if I just print this, so you would see like it's like a bigger string, and the action mask is like 1 for the end of those. So this is kind of fine, and this is and also like if I just show you the actions too, like it's just answer to, and now you can like append to this dictionary, and then again run it through this data collator and get the last assistant message, and you can keep on training. But there is a problem because this kind of this kind of tokenization is not helpful if your data is structured like this, like multi-step. So before diving into the example, let's discuss one more thing. What is the difference between multi-turn and multi-step? In multi-turn, as we saw, there is user assistant messages repeating. The user asks something, assistant responds, then again user asks something, assistant will respond again, and this keeps on repeating. In multi-step, however, there is repeated assistant message, like suppose for deep research or where you given a query and the model has to search the internet and get back the retrievals, and if it is not satisfied with the retrievals, then it has to search again. So there are no user responses there. It's just the assistant is looking at its previous message and then responding. So as I showed you in this multi-step message, so there is only one user followed by two assistant responses. So, and we would like to train on these two assistant messages because like this is what the model is generating for this user query. And now you can see a problem. If we had something a similar setup like this, then we will only train on the last assistant message, which we don't want. And it's kind of really difficult to like specify, okay, you just need this index, you want to train on only this index, or this is a multi-step example. And also I would like to suggest you guys go through this blog post. This is like a really good blog post on the exact problem that we saw. And there are also a lot of like in one of the blog post where from VLLM, you can see tokenization and retokenizations are sometimes problems. Like they can give you different answers. So just tokenizing the entire thing and then trying to find the response template IDs is not very ideal when you have multi-turn conversations or multi-step conversations. So as suggested in this blog post, they suggest of going incremental tokenization by tokenizing one string at a time. And this is the code. Like it's kind of overwhelming at the start, but let's go through it slowly. Let's first understand the flow of this code part, flow of this tokenization. So for each turn, we would first check if the current turn is train or the next turn is train. If neither the current turn or the next turn is train, then we just like skip it because it is like a system prompt. So we'll just like skip. If it is not a system prompt and maybe it's like a user prompt, and then is next turn train is true, so we will go here, we will apply chat template on this messages, and and then we would compare whatever we have till now. Like it's an incremental tokenization, so whatever you have till now, you just take it, and then you add in the next set of token IDs. So if the next set of token IDs that we'll be adding can either belong to the action mask of 0 if you don't want to calculate loss on them, or it can be 1 if you want to calculate loss on them. So this is how we'll decide, like action mask, if it is assistant then add 1 or 2, or if it is user then just add user, or tool then just add zeros. So incrementally we'll be going through each messages and then adding to see have we repeated anything till now. If not, then we just like add the actions, and we'll add the actions and the action mask. So now if I have to show you some examples, let's say we have this multi-step search R1 type messages, which looks like this. We have system, user, assistant, then you have a tool where you retrieve the documents, and then you do the language model generates again. So the entire prompt string would look like this. And if I just decode the actions, you would see this answer 1, answer 2 are only part of, they will be only considered for the loss. And also like if I just like multiply states and action mask, you would see like rest of them are zeros. So this exclamation mark means the token ID 0, and so we just like compute loss on these things.